and now you get, at the beginning, you get to have me looking at the camera confused a little bit. So before we get started, actually, a reminder just in case anybody is not aware, Exam 1 is Thursday, and it's at this time, and all of you in this class will take it at this time. You guys, mostly being the Tuesday group, will mostly be upstairs in the lab. I've got 3 or 4 who are quarantined still. That'll open up some space down here. We can put 30 people in this room. So there'll probably be like 12, 13 of you up in the lab. Look at the sign-up sheet. I'll have that divvied up there, like where you're supposed to go. Hey, make sure there's some of these, actually here. No, don't take that one, that's the key. There you go. Yep. Oh yeah, tons. So anyway, general advice for the exam. There's review tonight. So if you want to come tonight, same deal is going to apply. Like some of you are signed up for that. If you want to come and see if there's a seat, that's fine. It'll also be recorded and online. So at this point, you really should be down to work in old exams. There's a module, if you haven't found it, that's got a whole bunch of old exams. I would start at most recent and work your way back. I can't promise the coverage is exactly the same on all of them, but it's pretty close. Certainly if you look at last year's exam, it's going to look somewhere in the ballpark of that. I would recommend before Thursday that you take at least one of those exams under exam conditions, right? So find a quiet place where your roommate's not bugging you, you're not listening to music, you don't have a TV on in the background, you're just working the exam. Closed note, closed book, it's a live exam. Time it, and then grade yourself and see where you need to study. I'd probably do that before like Wednesday night or Thursday morning. That would be a good thing to do today. And you can hopefully then figure out that I'm really good at absolute configuration, I suck at chairs, whatever it is, and then you focus on the thing you're having trouble with. The other thing I'll recommend, it's a 12:30 exam, so this shouldn't be too big a deal. Don't stay up all night Wednesday studying for it, right? Like your brain is a physical thing. We all think about it as a mental thing, but your brain requires nutrition and soberness and sleep, good health. So get a good night's sleep, eat right, eat some breakfast in the morning. If you're a caffeine user, use some caffeine, but not too much. Okay, I'm verging on to grandpa territory. So take a look at that. If you guys are at home watching this, this is February 23rd, 2021. That file should be on a module. By the time this video is uploaded, this file will be on Canvas. So there's a whole bunch of questions there. Like I say, I think Exam 1 in Orgo is like the least, I'm not saying it's easy, but in terms of figuring out what's going to be on it, like there's a handful of questions that are going to be on it. So make sure you can do these. I mean, there's some questions beside this that you'll see, but there shouldn't be a whole lot of doubt as to what will appear on the exam. And I'm going to draw this thing on the board. And I left out a question. somehow managed to not, so in addition to all the questions on your sheet, I want you to draw the other chair for this molecule. If you haven't, you should probably fast forward. Everybody working from the top? Let's stop and do some of that, and then we can. I just told them to fast forward. Well, they didn't go too far. So let's draw the chair flip first. And before I get into that, green and red don't work. So the chair flip is a conformational change. It's a really unfortunate word. All right, it is so ingrained in organic chemistry lexicon that it's not going away. But a chair flip is not flipping the molecule over. And I'm going to try very hard, instead of saying flip the molecule when I mean turn it over, to say turn it over or roll it away from you, roll it left to right. Right? That's basically just taking a different perspective. And one of the things that's really important to understand out of everything we've done, there is no forced perspective. You can look at a molecule from any direction. You can look at it from above, below, right, left, whatever. Right? The molecule itself does not have an up and a down. So if I say a wedge is up, that's not some sort of magic like, oh, this molecule, like the wedge is its head and the dash is its feet. That is me saying the way I'm looking at this molecule, a wedge is up. So I know there was a lot of confusion on number one on the cyclohexane quiz, right? That there are, the wedges, everybody's like, the wedges have to be up. So the correct answer actually had the two groups down. But that's down as it's drawn. You could imagine rolling that molecule away, not doing a chair flip, not doing a conformational change, just rolling that molecule away from you, and now the two groups are up. It's the same molecule. You're just looking at it from a different perspective. Does that make sense? Right? Like if I asked you to draw a tree, I would imagine 100% of you would put like a fat trunk and leaves up above it. Because the assumption is you're looking at a tree in Earth's gravitational field. Like the trunk is at the bottom, the narrow part is at, high up off the ground. Molecules aren't like that. Right? They don't have a heavy part, they don't have a bottom part, they tumble around. So again, any perspective is fine. If I say a chair flip, which is what I'm saying here, it's an actual conformational change. Right? All the atoms are staying the same. So if we look at this chair, we've got a left-hand carbon here, a right-hand carbon. I call that the up carbon, but again, there's 3 up carbons. This carbon, and that one are all up. This one, and that one are all down. And if I wanted to walk over here 60 degrees, I could make these two the front, these two the back. This would now be the left hand, that would be the right hand. That'd be fine. It would be the same molecule, I'd just be looking at it from a different place. So when I say a chair flip, when I say draw the other chair, I mean an actual conformational change. And so this carbon will come up, this carbon will come down, the down carbons pop up, the up carbons pop down. And so that will get me all right, so this left-handed carbon is going to pop up. Now, when you do that, the relative orientation of groups doesn't change. So we've got a cyano group, a nitrile, in the equatorial position on the left-hand carbon in the original structure. But it's up relative to the other thing on it. Right? The other thing on it is this H, which is axial, which is down. So up and down aren't going to change. My perspective, the thing about your perspective is you get to pick it once. Right? You don't get to say, I'm going to draw the left-hand part of the molecule from this perspective, and then I'm going to walk around to the back of it, and I'm going to draw the right-hand side of the molecule. Right? You got to, once you pick your perspective, that's it. So if I say that the cyano is up, that means this H is down, and that stays the same through all this. So when the chair flip happens, the cyano pops up to the axial position. The H winds up in the equatorial position. All right? This carbon-nitrogen triple bond is called a cyano group. If you have it by itself and the carbon has a negative charge, it's cyanide ion. Bonded to a carbon, it's a lot less toxic. Right? So Cyanide is toxic because it binds the iron in hemoglobin. If that carbon is neutral, can't do that. All right, then if we go around the back, the other thing is to keep, we're not flipping the molecule over. We're doing a conformational change. So these two front carbons stay the front carbons. The two front carbons here don't have any substituents on them. They have 4 hydrogens, so 4 hydrogens here. The back two carbons, the one closest to the cyanide, has an amino group that's down. All right, the axial position for the up carbons will be pointed straight up. The axial positions for the down carbons are pointed straight down. So again, this has got to change. The amino group, when this group goes down, the amino group, and this can be a little hard to draw. The amino group should be going straight down. I don't want to confuse it there. So this bond is broken in the back. If you've taken any drafting, right? The front bond is in front of that bond, which is farther back. All right, so amino group is down on this position. Then the methyl, which is up relative to the carbonyl, goes from axial to equatorial. Our carbonyl pops down into the axial position. So there's your chair flip. And these actually go back and forth. We indicate that by these equilibrium arrows, 2 different arrows, one going left, one going right, which means these two structures go back and forth. Sometimes we have this structure, sometimes we have that structure. That's different than a resonance structure. Resonance structures don't go back and forth. They both exist simultaneously. All right, which one of those is more stable? So, larger group, yeah, larger groups in just number, right? So up here we've got, what do we have? Equatorial, equatorial, equatorial. So that's 3 equatorial, 1 axial. Down here we've got 1, 2, 3 axial, 1 equatorial. And so the only way, if you have that, right, the most, well, I'll get to that in a second. No, I'll say it now. So the most stable way to have a stereoisomer of this compound would be to have all 4 groups be equatorial. Is that possible here? Right. It's not possible because 2 of the substituents are on the same carbon. Right? So those 2 substituents can't both be equatorial. So 3 equatorial is the best you're going to do, and that's what you've done. The only way that the chair that's got 1 equatorial group could be more stable is if down here this 1 equatorial group were enormous, right? If this thing were super large, and these, actually cyano, amino are pretty small relatively, right? They're not that big. This carbonyl's a fair sized group, but if this group were something much larger, it might be more stable. Right? So judging stability is can be a fairly subtle thing. All right? It's exam 1 of your first semester in organic. I'm not going to give you a really subtle thing tomorrow, Thursday. Right? It's going to be pretty clear. I want you to know you want most of the groups equatorial, or you want the really ginormous thing equatorial. And if you can do both of those, that's what you want. All right. I'm going to give you 30 more seconds, then we'll do the bond line. There's been some questions about this one. I'll do this helpful thing for you real quick. Right, it's a chair, it's a cyclohexane. So bond line, it's going to be a hexagon. if you've got this, you can go ahead, and you haven't got the others, you can go ahead and do some of those other ones. Okay. So again, where you're looking at this molecule from and how you're looking at it is important to determine. The chair gives us quite a bit. It's telling us that these two carbons are the front. Again, the lower of these two, right, the two kind of middle bonds that are parallel, those are going to be, the lower one is in front. So our eye is closest to these two carbons. And again, I've got a hexagon here. It doesn't matter. You could say my eye is here and these are the front. My eye is here and these are the front. You can put, basically, you're going to be able to put your eye in 6 places. And then again, you could imagine, right, that you could imagine that, you know, it's sort of here and you're this way, or you could be upside down. I'm going to draw it usually, like I have a way I do it. And this is what I said at the beginning of all this, that like how I see things and how I take these little 2-dimensional squiggles on a board or on a piece of paper and inflate it into 3 dimensions in my head will not always be the way you do it. And there is no right perspective. There's just being consistent with your perspective. All right? So once you decide where you are, that's it. You've got to be there for the rest of the day. All right, so I am going to say that my eye is here and that up is a wedge. All right? And that this is, so I'm going to say up is a wedge. And I'm going to say that this is left and this is right. Okay, so we're going to have cyano is going to be up. These two carbons are going to be the front. Here's the front. So cyano is going to be up. The NH2 then is on the back carbons. Right? If I'm saying my eye is here, these are the back carbons. If my eye is here, it's got to be this one. So the cyano and the amino group, the CN and the NH2, you guys have to know the NH2. You don't have to know these other ones. So the amino group and the cyano group are trans, and they're 1,2. So cyano's up, amino is down. I'll look at my key and make sure I'm doing this right. All right. So then if we number these, and again, this is not necessarily, this is pretty close to how you do it. 1, 2, 3, 4, 5, and 6. So it'd be 1, 2, 3, 4, 5, and 6. So 5 and 6 are close to your eye. They're the front. 2 and 3 are the back. Amino's down on 2. Nothing's on 3. 4. And again, what's important here, wherever you picked your perspective, keep the cis-trans relationships the same, okay? Amino and cyano are trans, so there better be a wedge and a dash when you put them on the cyclohexane. Doesn't matter if you were upside down for me, it's fine, but you've got to have them be trans. The cyano and the methyl are cis, up and up, so 2 ups is cis, 2 downs is cis, an up and a down is trans. So the methyl is going to be a wedge, and that's going to make the other one I bet this is really readable at home. All right. By the way, just as an aside, well, I'll do it now I said that. You don't have to know this functional group on exam 1. You do have to know this one, and they're different. They've all got nitrogen in there, so this is probably bad pedagogy to try to confuse you. It's just another element. But the amino group and the amide group, amide, AMIDE, this thing, a nitrogen bonded to a carbonyl is not an amine. So the nitrogen on the right is not an amino group. An amino group has a nitrogen that's bonded to hydrogens or sp3 carbons. And we'll talk about that on the last question on this sheet. All right, questions about how I got to bond line there. So you could have drawn it upside down. You could have actually physically flipped this over somehow. Like, there's lots of different ways of doing that. Like, imagine, let's say we just flip the molecule over. Right? When you just turn it over, wedges turn into dashes, dashes turn into wedges, and things change sides. Right? So if you'd come up with that, that would have been fine. If you had rotated this 60 degrees, 120 degrees, 180 degrees, that would have been fine. All of those would be the same. So I use this analogy that all these structures are sort of a language, right? This is sort of the beginning of a language class. What are the words? What are the pronunciations? Where do you put the verb? That sort of thing. There's idioms, right? I can sort of do things my own way a little bit as long as I follow a few basic rules. And that confuses things. So if you've ever studied a language and then gone to a country, like, you know, if you take an English class, I'm not going to be able to come up with an example now. But you guys have done this. Like, if you hear how we're supposed to say things, it's very, you know, English has got all these rules. And on paper, all the words are separated from each other, right? Then you go into a bar or something, and somebody just, there's a string of letters. I don't know what that is, right? That actually, so having idioms actually confuses things a little bit. Being able, it's going to confuse you at the beginning. Being able to sort of turn these molecules around, turn them over, look at them from different perspectives. This would be easier to get if you always had to look at every molecule from the left hand standing upright, right? Just make sure you're picking out a perspective and staying with it. Sort of went through this. I basically gave this to you. Sorry, I'll give this to you fast. What you know here, what I would expect you to be able to tell me is that there's an amino group, all right? Nitrogen that is not bonded to a carbonyl is an amino group. I'll give you 15 seconds to add the lone pairs. Let's add them. I'm going to add them to this, the less stable chair over here. Yep.
Is saying it's an amino different than saying it's an amine?
No.
Okay.
Yeah. Amino, amine, yeah, those are fine. Sorry. There's not a carboxylic acid. A carboxylic acid would have an OH here. So there's a carbonyl, and then the functional group of a carbonyl bonded to a nitrogen is called an amide functionality. Yeah, carboxylic acid is carbonyl, CO double bond. That carbon is bonded to an OH. Yeah. In the six or seven that I sent out in that, there's a handout, yeah. So no, I don't know if you want to call it, you either benefited or didn't. If you think it's an advantage, you benefited. If you think it's a disadvantage, I kind of screwed you over. Normally, like the first day of class, I'm like, these are the functional groups you got to know, and there's 20 of them or something. And that goes on exam 1. Because I failed to do that this year, I'm interested to see if you guys, I'm going to sort of do, here's the exam 1 group of functional groups, here's the exam 2 group of functional groups, here's the exam 3 group, and maybe you guys will learn it better than they usually do. Like, it's certainly, you can break them down. So anyway, there's an announcement, if you dig back through the Canvas announcements, of which functional groups you have to know. I think it's like alkyl halide, alcohol, amine, carboxylic acid, Alkene, alkyne, I think. Yeah. For exam 1. We'll take it up a notch for exam 2. I'll put amide on there for exam 2. Okay, lone pairs. Hopefully you can do this really quick. What is the overall charge on this molecule? 0. There's no charge. I did not draw a charge on there. A molecule has to have charges shown. A correct structure has to have charges shown. I will tell you, and again, this is where looking at the old exams helps a little bit. There will be a question on Thursday where I've drawn molecules that have charge that don't have charges shown. And the reason I will do that is to ask you, look at this structure, what are the charges, okay? When I do that, I have to show you every atom and every lone pair. I can't say, what are the charges and where are the lone pairs? All right, there's an infinite number of solutions for that. So there will be questions where here's a molecule, all the atoms and electrons are shown, tell me the charges. This is not that. This structure, if there were charges, I would have to show them to you. And so I didn't. And so nitrogen, 3 bonds, a neutral nitrogen with 3 bonds, think ammonia, is going to have 1 lone pair. I'll go ahead and put them on this first one, whatever. All right, so that nitrogen has 1 lone pair. An amine group, nitrogen, 3 bonds, neutral, that nitrogen has a lone pair. There's a trend here. Nitrogen, 3 bonds, neutral, lone pair. It takes care of the nitrogens. The oxygen has 2 bonds shown, so it's got 2 lone pairs. Right? You're basically just making up octets for these guys. Make sense? Is that a hand up? Yeah, okay. All right, we did all that. Who's got a molecular formula they want to share? No one. Right. So these you should get, right? Like those are, you only got to count to 3. They stand out. You have to explicitly show those. Another little trick, you've got an uneven number of an odd number of hydrogens. I don't know if 19's right, but it's going to be odd. If you have an uneven number of nitrogens, you will have an uneven number of hydrogens, assuming there are no halides. There are all these little rules that are not like, there's always an exception or two. But if you don't have halides, and you have 1 nitrogen or 3 nitrogens or 5 nitrogens, you'll have an uneven number of hydrogens. So let's count carbons. 6 in the ring, 7, 8, 9, 10, 11. All right, we got the 11. I'm taking a lot of credit here. You got the carbon right. And again, right on the key, I didn't do this on the key. If I use ChemDraw, I can just get this straight away. That's how I would check you guys. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to come up. I missed the nitrogens, didn't I? Yeah. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 on the 3 methyls. So there you go. C11H19 N3O. I didn't ask, but how many units of unsaturation are in this molecule? Got to vote for 3. That's the leader because it's the only vote. This is how democracy works. One vote, that's the winner. You say 4? All right, we're tied at 3 and 4. Suddenly a breakthrough. Now it's 2 to 1 for 4. Anybody disagree with 3 or 4? Anybody think 2 or 5? All right, so you can go into this equation. There is an equation that will let you get it from the molecular formula. That's worth knowing that you can do that. I don't like doing that. I like looking at the structure. So what is an unsaturation? Pi bond or a ring. There's a pi bond, there's a ring. That's 2. How many are here? How many? 2 pi bonds. So it's each pi bond. It's not just that there's a pi bond there. So it's 4. All right, circle the sp2 atoms. 5 seconds if you haven't done that already. Circle the sp2 atoms. All right, that's 5. So carbons that are double bonded, carbons that are attached to 3 different groups, or the things that they're double bonded to. That oxygen is also an sp2 atom. I said atom, I didn't say carbon. So both of those should be circled, carbonyls. And that's it. Put a triangle around the sp atoms. 5 seconds for that one if you haven't done it. All right. sp atoms will be connected to 2 things. sp carbons will be attached to 2 things. sp atoms will be linear and have 2 things if you count lone pairs. So that nitrogen has a lone pair and a carbon. So the nitrogen is also sp. All right, we've done those. Assign absolute configuration to all the chiral centers. Let's blast past this. Is the molecule itself chiral? And again, that bond line might help you. I noticed a little bit of trouble. I haven't had a chance to really look closely at the absolute configuration quiz, but I noticed some trouble. There was a chair, right? That it was actually in a chair. And I asked people to assign R&S. The scores on that one were a little lower. But if you look at this, if you look at carbon 1 here, there's an H, a cyano, a CH, and a CH2. So that's a chiral center. Carbon 2 has an amino group, an H, a CH, and a CH2. That's a chiral center. Carbon 4 has a methyl, a carbonyl, 2 CH2s. So is that chiral? Yeah, you got to keep going. All right. So yeah, carbon 4 is bonded to 2 CH2s. But if you keep going past there, the carbon 3 CH2 is bonded to a CH. Carbon 5 CH2 is bonded to a CH2. Those are different. So this molecule contains chiral centers. The only way the molecule will not be chiral is if there is a plane of symmetry to it. All right? If a molecule has a chiral center in it, the only way for the molecule not to be chiral is if there's another chiral center somewhere that can kind of offset that first chiral center. So you need a lot of symmetry in the molecule. You need another chiral center kind of situated in the same place, connected to the same groups. It's a pretty rare situation. We hammer it hard as a concept in Orgo 1. If you go into biochemistry, you may never see another one. All right? Sometime when we do synthesis, it's easier to make a small molecule symmetric than a giant molecule, right? And biochemists tend to work with really big molecules. All right, so this compound is not meso. This compound is chiral. All right, so draw the enantiomer if you haven't already. If you have drawn the enantiomer, if you drew the enantiomer in the bond line, draw it in the chair. And if you drew it in the chair, draw it in the bond line. Oh, sorry. I might. I mean, so that's, other general instructions for an exam. Read the instructions and do what I say. I can tell you from my grading, like you guys are almost certainly going to disagree with this, but I feel like I'm a pretty laid-back grader. I promise, there's no one in here that will believe that on Friday. But like even if I said draw the enantiomer in the chair form and you drew the bond line, like I'm not going to, if you draw it correctly. So if you don't follow the directions and you screw it up, there's very little partial credit going to come. But if you can draw the enantiomer and you know it, like what do I care about? Right? Deep down, I don't care how many points you get. I care, do you know what an enantiomer is and can draw it? And like I said, really, if you think about it, chair versus bond line is also just a perspective change, right? Bond line is I'm looking at it from above. Chair, I'm looking at it from the side. I don't care. Yeah. So usually if I say draw the enantiomer, give it to me however you want. Yeah. Some people, so it kind of would depend. If this were really a problem, and let's say I had not asked you to draw the bond line, right? So if the first thing I did was draw the enantiomer, probably the easiest thing to do is actually literally draw the mirror image, all right? And we can try that. So we don't have a bond line there. All right. So again, rather than trying to convert this to a bond line, so personally, I feel like it's easier to draw an enantiomer from the bond line. You just keep everything the same and switch the wedges and dashes. Easy. All right. I would actually then, but if I had a chair, rather than go through it, like if I try to convert the chair to a bond line, that's something I have to do. It takes some time. I can screw it up. The number of things you do increases the chances you'll screw something up. That's true in everything. So if I can just draw the mirror image, of course I have to be able to do that. All right, so there's the mirror image for everything, but the amino group's going to stay in the back. It's going to go over here. And I get that. All right, so there, I've drawn the enantiomer in the chair. Of course, if I do have the bond line, all right, so there's my bond line structure. Now when I say keep everything the same, so I'm just going to recopy all right, there are my groups. I'm going to change a wedge to a dash, NH2 to a wedge, or the dash to a wedge, dash to a wedge, wedge to a dash. Right, so, like I said, I find it easier to draw the enantiomer from bond line. So if I had that and was confident in it, I'd probably draw that. And since I know you guys are interested in grades and stuff, if this was an exam question, and you guys had come down, like I did this in order. I say draw the bond line. Let's say you screw this one up, but then right below that is draw the enantiomer, and you draw the enantiomer of this one, you're going to get some credit for that, right? Like I try not to nest things. I always hated those as a student. I hate those kind of things in life where if you screw up here, you've screwed up forever, and you can never be redeemed, right? You missed part 2, so the hell with you. So I try not to do that if I can. Yeah.
Could you also just actually do the mirror image?
Of the bond line?
Yeah.
Yeah. Yeah, absolutely. Right. So like I said, and oh sorry.
In the chair confirmation, can you switch the active and oil?
So you could do that. Yeah, that's a good question. It's important to know what this does. So if let's see here. So let's take our less stable conformation. Right. You can see that the chair has actually flipped as well. If I draw the chair the same, right? So now my chair is the same, but I switch axial and equatorial. That's the enantiomer. Why is that the enantiomer? Yeah. This is the equivalent of switching wedges and dashes, right? So up becomes down, down becomes up, down becomes up becomes down. Yeah. What you want to avoid doing, well, so that's the other thing. If I ask you to draw both chairs, like the original question, don't do this. If you keep the chair the same and switch equatorial and axial, you're drawing the enantiomer. If it's an achiral molecule, you get lucky and it works out. Right? An achiral molecule is a lot easier to deal with than a chiral molecule. Where are we? Right. You can draw the mirror image of the bond line. Yeah. But again, you have to choose which one you're doing. If you draw the mirror image of the bond line, all the wedges and dashes stay the same. If you draw the mirror image and change the wedges and dashes, you're just flipping the molecule over, and you get the same structure. Right? So you have to choose which approach to doing the enantiomer you're doing. Changing equatorial to axial is changing up and down. All right, so I think that's good. We're moving along. Does a diastereomer of this molecule exist? I missed a question somewhere, I think. Oh, absolute configuration. Before we get to diastereomer, how many stereoisomers does this molecule have? It has 8. This is also kind of a goofy English question. How many stereoisomers does this molecule have? Everybody says 8, 2 to the 3. But one of those is this one. I will be pretty lax on this as well, right? If you tell me that one has 7, like I try to ask it like how many stereoisomers for the overall structure, because my point is of the 8, one of them is this one. So like this one has 7 other stereoisomers. It's a chiral molecule. In fact, every one of the 8 is chiral. So what we really have is 4 diastereomeric pairs. Sorry, 4 enantiomeric pairs, right? So we have this one, it's an enantiomer. Then we have 6 diastereomers. Each one of those diastereomers has an enantiomer. So if you haven't, I'll give you a couple of seconds to draw a diastereomer. If you've drawn a diastereomer, draw a different one. All right, there are 6 on the board, so I'm missing 2 at least, assuming I didn't double them up. I didn't do this one before I came in either. Diastereomers are not or they're stereoisomers that aren't mirror images, so they have to connect the same all the way around the ring, or it doesn't have to be in a ring. It could be an acyclic compound. in the reflection, all the chiral centers will switch. R changes to S, S changes to R. All right. For a diastereomer, there are 3 chiral centers. At least one has to change. At least one has to stay the same. Okay, so you could have 2 change, 1 stay the same, 1 change, 2 stay the same. Over here, we've got a trans amino group. Amino and cyano are trans, so they got to be trans in the isomer. Amino and methyl are cis, so they got to be cis in the enantiomer. These are the 4 structures that have cyano and amino cis. And so the other one ought to still be trans. So let me get my... And so the amino and the amide are cis over here, so they're going to be trans on this one. Sorry for the ugly drawing. And then invert that. All right. All right, so 4 enantiomeric pairs. Yeah, sorry. No. I'm showing off. Look what I can do. I have very few skills or positive attributes, so being able to draw a lot of stereoisomers is good. Yeah, so I said draw. All of you should have drawn one of those. So if you look at old exams, I usually say if there's a diastereomer, draw one. Be careful. Just because I say if there's a diastereomer, draw one, there doesn't have to be a diastereomer, right? So there doesn't have to be a diastereomer. There doesn't have to be an enantiomer. Constitutional isomer, there's only 8 stereoisomers. There are literally, 10 to the something constitutional isomers. Move one thing. Easiest thing to do here would probably be, I don't know, move a methyl off this nitrogen onto the ring, move the methyl to the carbon here, move this methyl that's on C4, move it over to C5, whatever. And again, it's easier for me to grade if you make a very small change. If you want to get creative, you got 20 minutes left in the exam, this is all you got to do. You've got a molecular formula, have fun with it. Right? But again, I'm going to count. I don't have a lot going on, so I'll count and see if it's actually a constitutional isomer. It's easier to come up with it if you make one simple change. Any questions on the stuff we've done up to now, and then we'll do absolute configurations. Any questions on anything else? No, I said it was. Somewhere, yeah. This is an overall chiral molecule. Yeah. So an example of a meso compound would be, I've drawn quite a few. Right? That compound is not chiral. There's a plane of symmetry right here, but there are 2 chiral centers. That carbon is bonded to an OH, H, methyl, and then this other thing. Right? So it's bonded to 4 different things. But you've got 2 kind of identical chiral centers that offset each other's asymmetry, if that makes sense. Yeah.
What if one was dashed? It wouldn't be...
Right, if it's dashed, it's not.
Okay.
It still looks like a really symmetric molecule. And you just kind of have to play with it at that point and well, no, it's that, so the thing is, right, if you look at the mirror plane of this, the left side is exactly the same as the right side. If it's a dash, they don't perfectly reflect into each other. Okay, actually, before we get to absolute configuration, have you come up with a resonance structure? Right, there's only one place you can really do that, and this is why an amide is not an amine. All right, so I know green and red don't show up that great, but I'm going to use them anyway. Over here in the amide, we've got a lone pair on nitrogen bonded to a double bond. Right? The lone pair on the cyano can't really do anything with the carbon it's bonded to. I'd make 4 bonds to that carbon. You can actually draw some resonance structures on that cyano where you just take like one of the pi bonds, put those 2 electrons on nitrogen. You get a positive carbon, a negative nitrogen. That's a resonance structure. Something that came up on the resonance structure quiz. Let me put in lone pairs. That is a resonance structure. You can take the 2 electrons in a bond and homolytically break them. So if you've got a pi bond, you've always got a resonance structure where you can take the 2 pi electrons, put them on one atom, and you get charges. Or you can take one electron on the pi bond, put it on one atom, put it on the other, and now you've got neutral radicals. All right? Electrons do not have to be paired. They are paired, electrons are paired in stable isolable molecules. Okay? So there are a lot of molecules, and we'll do some right at the end of the semester with radical chemistry. But radicals tend to be really highly reactive, even though they're neutral. So I think some people got in AP Chem or General Chem that you can't split up a lone pair. You can. Yeah. No, it turns out they're neutral, right? Like if you do this, formal charge on the carbon is going to be 4 minus a half of 6 minus 1. So it's 0. Same thing on the oxygen. And you can think about that, right? If I'm when you do the formal charge calculation, you assume half the bonding electrons, you assume the bonding electrons are shared equally. Right? So then if I formally do that, I break that bond, and I put half the electrons on one atom, half on the other, my charge doesn't change. So that's not a super significant resonance structure, but it's a legitimate one. But we've got one really good one in this molecule. Fumble. So let's look at the resonance structure, and then we'll do absolute configuration. And I'm gonna short circuit the molecule. Right, so here we have a lone pair bonded to a pi bond. So we can use the lone pair on nitrogen to make a pi bond. That carbon can't have 5 bonds. So if we make a 5th bond there, one of these bonds has to break. All right, and so then our resonance structure looks like this. You got to put the charges in. Again, for a resonance structure, the overall charge doesn't change. So it's neutral on the left. It's got to be overall neutral on the right. But you can introduce loads of charge in the structure, in the resonance structure. I bring this up. Again, this is an amide functionality. You'll hear this over and over, but it's good to get right now. It's also known as a peptide bond or an amide bond. So our proteins are made up of amide bonds. Amino acids polymerize to make amides. And if you take if you get a crystal structure of a protein, the carbon-nitrogen distance looks like a carbon-nitrogen double bond. The carbon-oxygen distance looks like a single bond. The oxygen, this carbon, the CN and the double bond, the 2 methyl carbons, all planar. All right, that is a really significant resonance structure for an amide. And I know you should absolutely go into exam 1 thinking, if I'd given you that, the first one is better, right? Every atom's is neutral. It just turns out that in that amide resonance structure, that's really good. You've essentially, what you've got, and again, if you think about molecular orbital theory, I hear you guys don't like that. But if you think about it, we're trying to do Lewis structure. This lone pair is not localized on the nitrogen. It's delocalized over an N, a C, and an O. The more electronegative of those atoms is the O. Right? So if I'm going to share electrons over 3 atoms and one's an O, it's probably going to be on that O. That's deeper than you need to be. Like I said, the thing you need to spot here is lone pair next to a pi bond. If you have a lone pair next to a pi bond, a charge next to a pi bond, that can delocalize, right? You need that pi bond there. Yep.
Would it be a significant, but can you just use the leftmost arrow just to make the oxygen?
Yeah, so there is another resonance structure here, and it's fine too. And here, again, the thing is, right, you can always do this with any pi bond. And that turns out where you have a positive carbon and a negative oxygen in a carbonyl, any carbonyl, turns out to be a significant resonance structure. Like if you look at the geometry, it doesn't look like that. But if you look at the chemistry, right? So this carbon, the carbon of a carbonyl reacts with negative things. The oxygen of a carbonyl reacts with positive things. So this structure does actually explain the chemistry of the carbonyl pretty well. And again, these are all resonance structures, all right? The molecule's not going back and forth between these. All 3 of those exist simultaneously. Someone asked me what you need to know of molecular orbital theory on Thursday, and the answer is not much. All right? You need to be able to identify hybridized orbitals. That's not really MO theory. You need to be able to draw resonance structures, and resonance structures is a way to sort of approximate MO theory with Lewis structures. It's a fudge. All right, that's really all I'm going to ask. I like to bring in MO theory at the beginning because down the road, those of you that continue, any of you who become chemistry majors will see it. Any of you who go into molecular biology or biochemistry where you're doing sort of higher end chemistry things, you're going to see MO theory. MO theory is a much better theory to explain the behavior of chemical compounds than Lewis theory. It is a lot harder to apply with a pen and paper, right? And for most molecules, the stuff we learn in here, pen and paper, draw this, flip it over, that all works just, it gets perfectly close enough. But if you need a precise answer, especially if you have resonance structures possible, MO theory is what you have to use. And I just don't want you, so it's not going to really show up on exam 1. But I don't want you guys, getting 5 years from now, you're starting a grad program and you're like, Dr. Jones never told me about MO theory. Maybe you don't think that's a risk. Maybe you think I should be willing to take that risk, but anyway. Absolute configurations. Take a couple of minutes to look at it. Let's go back to here. I'm going to clean this up some to where we have the bond line and the chair only. All right. Back in the before times, I probably would have had like a giant thing of hot tea during this class. So I know I'm technically allowed to drink. I'm well separated from you, but anyway. Okay, so what are they? Got 3 chiral centers. don't have them on, if you don't have them identified, identify them by number here. So I've said this is 1, 2. So 1, 2, and 4 are the chiral centers. Did I do that the way it would be? No, crap. I totally did not do that. If I did this by nomenclature rules, which carbon would be number 1? 4. Carbon, what I've written is carbon 4. I forgot there's 2 substituents here. So I did 1 because then you get 1, 2, 4. And that's better than doing 1, 2, 5 or 1, 3, 4. But, so on a ring, right, every substituent could be 1. So the second substituent is what you want to look at, and the second substituent is that methyl, right? So the carbonyl is going to be 1, and then the methyl, so you have a 1, 1 setup. Don't dive too deep on the nomenclature. Okay, so, but for now, let's just stick with the numbering. You should be able to tell me if carbon 1 is RRS, carbon 2 is RRS, carbon 4 is RRS. How many of you working this worked it with the bond line structure? Yeah, that was the end of the question. How many used the chair? That's a pretty even split. So I'm going to do it with the bond line. I'm going to erase these numbers because we're going to put some priorities in. That'll get confusing. All right, so it's always easiest if you have the 4 group back. And if there's a hydrogen on a chiral center, that's going to be the 4 group. So as we look at this chiral center, carbon, carbon, carbon. That's a tie. All right, so then you go another atom. You're going to write down what those atoms are bonded to. This carbon is bonded to a carbon and 2 H's. This carbon is bonded to a nitrogen, a carbon, and an H. Sorry. What is that carbon bonded to? 3 nitrogens. N, N, N. Right? And then you compare the top line. N beats C. N ties N. So, right? The hydrogen's 4, this is going to be 3. And now you've got nitrogen versus nitrogen, that's a tie. Nitrogen versus carbon, so this is 1, and that's 2. And like I said, when you have the 4 group already away, you don't have to do anything else. The 1, 2, 3 works out. This is a clockwise circle. So carbon 1, or yeah, the one I'm saying is 1. The one with the cyano group on it is R. That's very messy now, so let me recopy it over here. And I'm putting in the stereochemistry of these other groups. Doesn't actually matter. Right? It doesn't matter. The stereochemistry I write here or here does not matter in terms of figuring out what the absolute configuration here is. Just to keep yourself from getting confused, don't change it. So, got an H on a wedge. So if we run through that, H is going to be 4. NCC, so N is 1. Carbon and carbon. This carbon is bonded to a carbon and 2 H's. This carbon is bonded to a carbon, and an H. Carbons tie. Carbon beats hydrogen, carbon beats hydrogen, so 2 and 3. You guys follow it? I did that fast, but that makes sense? So what is it? I got some votes for R. Anybody disagree? Right. So I was trying to trick you there, right? 1 to 2 to 3 here is counterclockwise. And this is, I screw myself up doing this. Like formally, you should redraw the molecule so that H is back, and then take the 1, 2, 3. If I flip that over, right? if I take a clock and I turn it over, it's no longer going to run, from my perspective now, it's not going to run clockwise, it's going to run counterclockwise. Seriously, that's a really fun thing to do. Power goes off, get your battery operated, real old-fashioned clock, and watch it from behind. Pass loads of time. All right, so 1, 2, 3 here, but the 4 group is sticking out at us. So take the reverse. This is also R. All right, one more to go. Wedged methyl, carbonyl, cyano, amino. What's the 4 group? The methyl is 4. Right? So if we look at this, chiral carbon, 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 carbon. That carbon is, the chiral carbon is bonded to 4 methyls, or sorry, 4 carbons. Right, again, you have to keep going. All 4 of those carbons are chemically different. So you have to go to the end of the molecule, or if it's a ring, get back to determine that they're the same. So then that methyl is bonded to 3 H's. This carbon is bonded to OON. I keep screwing that up. I got that right, didn't I? Yeah. I did this in an office hour the other day. I had nitrogen, oxygen backwards. CHH. CHH. So again, you got to go one atom at a time. Don't try to eyeball it. If you eyeball this, you're probably thinking, look at all those heteroatoms. And the NH2 over there, that's probably going to mean something. One atom at a time. O beats C, beats H. So this group is 1. H loses to everything, so that's 4. CHH, C's tie, H is tie, H is tie. So that's a tie. So now go to the next thing. They're each bonded to 1 carbon. So this carbon is bonded to a C, an H, and an H. This carbon is bonded to an N, a C, and an H. N beats C. So this is 2, and that's 3. Questions? So now it's the same thing. 1, 2, 3 is counterclockwise, but the 4 group is in front, so we need to take the reverse. So that is also an R. Yep.
And so then if, like, I did it with the priority 1 being that what you have 4, everything would be S.
Nope. So you're saying if this was a wedge, or sorry, if you're saying the dash was over here and the wedge was over there?
Like, yeah, so like that's on top of
Let me, yeah, so this is also going to be R. This is the same structure. This is one of those things that's, I think this is what you're asking. So if it's not, I can try better to get your question. No, I am screwing that up. Yeah. So that's what you drew?
No, like completely flipped. Like that's on the top.
Oh. So you drew this as a wedge and that as a dash?
No, like the oxygen is on like the top carbon of the ring.
Oh.
Yeah.
Sorry. No matter how you draw this, they should all 3 be R. All right, so this comes back. That's a better question than you asked. Let me go back to the question I was answering. I get this a lot of times, right? It doesn't matter if the wedge is on the left or the right and the dash is on the left and the right. In reality, they're directly in front and behind of each other. All right, now your question, no matter how I draw this molecule, from whatever perspective I look at it, so the word absolute is in there for a reason. No matter how I draw it or look at it, those 3 chiral centers have to be R. If they're not, you either have a diastereomer or an enantiomer. Okay, and once you've done this now, you can actually go over here and really quickly figure out what the chiral centers are. So let's do one. Let's do this one. Do R and S. For that one, I just circled in green. Don't figure it out. Look at this one over here. You got a minute. I've called 60 seconds on the exam. You have this structure and you figured them out. So R or S. Okay. So the quick way to do that, once you have this, assuming you have this correct, all right? And seriously, if I've called 60 seconds, assume you have it correct. So right here, we've drawn it with, now if you look at it, you've got the cyanide on the top, the amide on the bottom, the amino group on the right. Cyanide's a wedge. Oop, we changed it. Cyanide's a dash. That's going to be S. Amino group, we said that's R, and it's a dash. The amino group is a dash. It's a dash, so that's R. Methyl is a wedge, and it's R. On our green structure over there, methyl's a dash, so it's S. Right? When you switch the chiral center, and you could do that if you guys worked it out. If you worked out R and S for the chair, the original chair, you should have gotten 3 R's. If you then switch equatorial and axial for all those, you should get 3 S's. Right? The enantiomer of RRR is SSS. The diastereomers, one has to change. So, right, if a dashed cyanide is S, this one would be R, this would be S, this would be R. Remember, these are an enantiomeric pair. S has to become R becomes S becomes R. All right, once you, like, if they're, I mean, this, I would be a right bastard if I did this, but if I said draw like 16 stereoisomers for something, they're 4 chiral centers, and draw R and S for all of them, all I'm asking you to do is to figure out 4 absolute configurations. Because once you figure out those 4, they propagate. All right, and again, in terms of partial credit grading, like let's say you miss one. Like on the original one, here's my molecule, I think this one's S, but I got it wrong. Right, if you do this propagation method, you're going to get it wrong on every one of them. What I would be looking for is, are you going to be consistent there? Right, in the enantiomer, when you draw the enantiomer, they better all change. When you draw a diastereomer, one needs to change, one needs to stay the same, and you know, in between. I have lab. Any other quick questions? I'll do an office hour tomorrow. Mo's got a practice exam for you tomorrow night, I think. There are practice exams in the Exam1 module on Canvas. Definitely work on those. Shoot me emails. I'm behind in lab. If you have me in lab, I'm really sorry. I'm really behind in lab emails. I've been doing this class and another big project. I'll get those done. Study, don't study in like 8-hour blocks. Study in 45-minute blocks to an hour. Eat right, drink right, get some exercise. See you on Thursday.